So, let me say that way.
Okay.
So that's my side. So we welcome today our two speaker is Samuele Ferri from the University of Insubria, Como, to be more precise. And Samuele is a young researcher, but is obviously very gifted. He is still involved in some project maybe with Gabriella Bretti. And so his today's talk is a level set ghost point approach to PD. The floor is yours, and put question in the chat if you have any, and that question, please.
Thank you, Nicola, for the presentation and for the opportunity to be here and present a piece of my research. So, the title of the seminar is A Level Set Ghost Point Approach to PD. Actually, this seminar is going to be a useful talk for you to share, and a useful talk to share this kind of techniques you can apply in your future projects, which are the level set method and the ghost point strategy. But later we will see a combination of both in an example. Just to give you a bit information about me, I'm just a second-year PhD student at Insubria University in Como. My research topics are numerical approximation of PD for cultural heritage, but also I'm interested in multilinear algebra and GLT theory. And with Professor Sara Capizzano, we have these two papers. One is
what is GLT?
Generalized local interpret matrices. It is a theory about a sequence of matrices which are not triplets, and then they approximate PDEs and something else. But also, I'm interested a bit in differential geometry. So let's start. Let's start everything with the table of contents of this presentation, which is split in three parts. The first part, we see what are level set based schemes. The second part, we see the approach of the ghost point strategy. And on the third part, we see implementation of these two strategies. Let's start with the first one. So the basic idea of the level set method is just to solve PDEs on domains that are not necessarily conforming with the Cartesian grid we are using. So suppose we are in this situation. So the white grid is just the Cartesian grid we are using, but the domain of our problem is actually the red line. And so it can be, for example, cellulars, models, or a different shape for a pillar or a statue or something similar. So actually the problem is how to discretize and solve a PDE in this kind of framework. Actually, the red line can be interpreted as a curve of an higher dimensional surface. And with this idea, we split the domain, our computational domain, in three parts. We have the external part, which is the white one, the internal part, which is the light blue one, and then we have the boundary, which is the red line. The major problem here is that how to classify this kind of domains, of subdomains. Actually, we use a function called the level set, which is the phi function, and we say that the internal part of the level set is the region of the plane of the space where the value of phi of that point is lower or equal to 0. And in this framework, the external part is the region where the phi is positive, and the boundary is where the phi is equal to 0. So actually, the level set can be also an implicit curve, because with implicit curves we try to find the region of the space of the plane where the function is equal to 0. The problem is, okay, we have split our domain, our computational domain, in 3 parts. How we discretize our equation of PDE inside these 3 parts? Well, on the external part, we don't do anything, because our PDE doesn't exist outside the domain. In the internal part, we have to see if we are near the boundary or away from the boundary. The major problem is, okay, where suppose we want to discretize some kind of PDE, for example, a diffusion, okay, and suppose we are using finite differences. So we need a stencil. We need a number of points to discretize the second derivative. And so in this case, in the internal part, we use this kind of points. Now here is our two-dimensional draw, but you can imagine also this in 1D. And if all the 3 points or the end point of the stencil are inside, there is no problem. We can discretize with the standard discretization, and with the term standard, we just say the way we want to discretize, because there are many methods to solve PDEs and discretization schemes. The problem is when one or more points of the stencil goes outside of the domain. In this case, we need to firstly classify the points on the external part of the domain, and then find a way to use actually this kind of points. So in this framework, we say that a point on the external part of the domain, which is near to the level set, the function, is called ghost point. It's just a nomenclature, but you need to imagine that around the blue line there are many points according to the grid we are using, and the one which are near the nearest point to the blue line are called ghost point. In this picture, you can see only one, but in the next picture we have a better picture. It's because the blue points are the internal one, the black points are the external ones, and the red ones are the ghost points. So since on the ghost,
what is the definition of ghost point?
They are
live outside,
but they have in their neighborhood, in only the on the dimensional of the stencil, they have at least one internal point. So for example, this point is not a ghost point because we don't count the diagonal direction. We just use the standard orthogonal directions. And so this point is outside and we don't do anything. This is the definition of ghost point.
Only 2 questions. The first one is, so we are trying to enforce the boundary condition of the problem on the segment, let's say, that connects the ghost point with the internal point, right?
Yes.
And the second thing, I would like to know if there is any requirement for the T function defined earlier.
Actually, the only requirement you can have is just that it's the norm of its derivative is 1, just because you avoid to normalize the normal in the next step.
Okay, just because otherwise you can also make, for example, the modulus and the surface equal to 0 only to be accounted for.
Yes. So,
you are solving for phi, the work function over the domain.
Yes.
Outside and inside. So typically the real boundary is the boundary of the outside the domain, and the square, the big square.
No, because we just with this picture we just say that our domain is the blue one. We embed it in a bigger domain just to have more points and use the nearest point to the boundary to discretize the boundary conditions. The other points are useless, and actually you can cut the external shape and have something better, but in this way.
So you are not interested in the value of phi in the white part.
No, actually I use the phi value in the white part to classify the white part, because the phi value in the white part is positive.
Typically you solve in the whole square.
Yes, but you can have there are situations where you can have also an explicit version of phi. In the first example, I can show you how we use an explicit phi to define our computational domain.
Okay.
So let's go back here. So since we need the boundary point, a boundary point, because we can't use the ghost point to discretize the boundary condition, the only way to use this is just to project the ghost point along the normal direction of the level set. So we just take the point G, we discretize the normal direction with the values of the level set, and then we project using, for example, bisection method or other methods to find the point HG. And then we can use it because it is a point on the boundary. But the problem is this point not always is aligned to the grid. So how we manage to use this? And this is where the ghost point strategy is very useful. So we are in the situation where we have a problem with a boundary not conforming with the original grid we want to use. And so for each ghost point, the only thing we can do is interpolate to find the best situation, the best point to have the value of the function on that point. And so for each ghost point, we need a suitable stencil, and by suitable we mean that it has only internal points or ghost points. And then we solve the linear system associated to find the interpolation weights, and then we discretize the boundary condition using these interpolant polynomials. Okay? So, for example, if you want a second order accurate boundary condition, for each ghost point G, we select a 3x3 stencil composed of ghost points and inner points 3 times 3 because we want to use the Lagrange basis functions, which are the easiest to use. But also, you can use any stencil you want and any basis you want. You just need to keep in mind that you have to pay the computation of solving a linear system with the van der Monde matrix to find the weights. And then we find the B-quadratic polynomial, let's call it P, and then discretize or the Dirichlet boundary condition with the point HG, or the Neumann boundary condition using also HG, but also the normal, because the Neumann boundary condition uses a direction. And so we have a bigger system which has the PDA discretization at internal points, which is the standard one, but we add all the equations regarding the boundary condition for ghost points. But actually, maybe this could be hard to solve. You can apply strategies to preconditioning the system, but we wanted to show you a bit of workaround of this. Suppose, for example, to be in 3D, and we want to discretize this Robein boundary condition. Now we are not interested in the PDA we are solving. We just want to discretize this kind of boundary condition. And I put this boundary condition because it's the most complete. The application to the standard Dirichlet or the standard Neumann is straightforward. Here, the capital F means just a constant, but it can be a function depending on the value of x. Suppose we want to discretize this boundary condition with a quadratic interpolant polynomial. So we fix, again, a stencil, a 3 × 3 stencil composed by points of u that are ghost point or internal points, as before. And then we discretize the boundary condition using these formulas, which is the standard interpolation way to write an interpolant polynomial. Okay? With omega n, we means that they are the weights for the Neumann boundary condition, and with omega d, the weights for the Dirichlet boundary conditions. So we put everything together, and we rearrange the equation, and we have this situation that resembles a linear system. Okay? And actually, what we do is yes, yes. Actually, we split the matrix W into different matrices, the matrix H and the matrix K. Now, I will explain each element. The next slide has a picture of them, because it is a bit hard to understand at the first time. So, the matrix H is the matrix of the ghost points. So, on the ith row, we have the value Wij, if and only if the value, the node uj is a ghost point in the stencil we are using. Otherwise, is the standard vector of all 0 except 1 in the position I. While the K matrix is the matrix of the internal points. So, as before, it has the value of Wij if and only if uj is an internal point in the stencil, and it is minus ai hat otherwise.
One question.
Yes.
So why do you have like -1 and 1? Can't you just use like 0?
No, because we wanted that. Actually, you can have it, but we wanted to avoid matrices with 0 as a value in the diagonal, and also because we want just these two matrices, they can sum to W.
But if it's like a very huge system, wouldn't it be beneficial to have zeros, because then it would be sparse? Yeah, like...
Yes, it is possible. This is not mandatory. They are different. You can also use, for example, 1/2 and -1/2 or other constants. Yes. This one.
So omega n and omega d. These are the weights for the points regarding the boundary condition of a specific point.
Yes.
Which how are they evaluated in this?
In the practical, you can use the weights are in our implementation. We just use the Lagrange basis functions, and we use them to.
Okay.
But you can use whatever technique you want. You can also use the standard the quadratic polynomial basis. But you need to solve a 6 times 6.
They are the coefficient you should plug into in order to read the equation. And also, the Robin boundary condition doesn't use some constant, because it should be a linear combination of f and x.
Just to simplify here, just to be easier in this condition.
Source plus something.
Yeah.
Combination.
It is just a simple example. I just want to show you the technique. So these are the two matrices according to the previous construction. So the H matrix has 1 on the diagonal, except of these points, which are the weights of the interpolation, and the K matrix is the same. Also, the K matrix is a matrix that can have 0 in the diagonal, but luckily we don't want to invert this matrix, so it is not a problem. The major problem is the H matrix, if it has a 0 value in at some points in the diagonal, but this doesn't happen. So going back to the linear system, we just plug h plus k in the description. We just split everything, and what we want, we rearrange the terms, and we want to solve the final system with respect to the matrix H and this new right-hand side. In this way, the new vector of U star is a copy of the original U, which is the initial condition or the solution at some points in time, except the ghost point value. So we have constructed a virtual copy of the original vector of the solution, the approximation. And what we want actually is to use this U star, because we use U star in the discretization, and we multiply our scheme, our matrix with these values. Actually, we replace, or better, we store in the ghost points the values of the approximated solution at the boundary points. Okay, we just do this, but actually it's just a virtual point. We don't say that the solution at the ghost point is this. This is just a virtual value to be used in the computations, and to manage better all the geometry of the boundary. So let's go to the last part, which is a list, or better, a couple of example implementations. The first implementation is a work that is currently in progress with Gabriella and also Elishan, and we want to create a new model for erosion caused by inhibition. We want to create this new model, to study this new model, because this is the first approach of this kind of modeling problem for the erosion caused by the acidification of the stone with the water that goes inside the stone. So actually, what we want to study is, okay, the water goes inside a stone, a porous media, by filtration or inhibition. How it erodes? How does it erode the stone at the boundary and also inside? And so the system is composed by three equations. The first one is the equation that describes the evolution of the porosity. Okay, and the second is a non-linear equation that describes the evolution of the humidity inside the stone, and the third one is the evolution of the reaction, of the chemical reaction of the carbonic acid inside the stone. So actually our variables are n, the porosity, which in our case means that if the porosity is 0, the stone is full, or the locus is full, and if it is equal to 1, it is empty. The theta is the humidity, and the Ca is the carbonic acid. B is a function that describes the inhibition, describes the inhibition, and actually it is calibrated from some parameters and some realistic data. We add to the system these two boundary conditions, which are Robin types, and where the two Ks, Kw, Kc, they are the reaction rate of the aggression on the the exchange rate with the external air of the humidity and the CO2, the carbonic acid, and theta bar and Ca bar are just the values outside of the boundary, which is the most of the air or the pollution at some point in time. Okay. Just to, here is the list of parameters we see in the previous slide. The two cases are the exchanger, rho 0 is the density of the stone, D is the diffusion coefficient, and the two variables are the parameters outside. Just to give you a small insight of the B function, the B function is the orange one, which is the almost parabola function. The blue line is its derivative. So actually, the important thing about the B function is that the reaction happens only on a smaller interval of its domain. Here, the values 0, 0 point, etc., they means theta divided by the porosity. Okay, and also the B function has one point, which is here the highest exchange rate for the inhibition. To discretize this system, we use finite difference scheme with implicit Euler method. So the first equation with the porosity, actually, it is easier. It is the easiest, actually. And humidity, we just discretize the diffusion with this operator, which is in the next slide, and I show you in a couple of seconds. And the third one is the most complicated. So actually, since the equation regarding the carbonic acid is a diffusion reaction equation, we discretize the diffusion with the standard second order finite difference scheme. And the reaction, we use this operator. Actually, since this example is in 3 dimensions, delta ijk is the sum of 3 different sub-operators, let's call so, but it is just this kind of approximation. Delta I uses the discretization on the I direction, delta J uses the same but in the J direction, and K in the third direction. Okay. Also, in this scheme, we add this term, which is a second order discretization of the artificial viscosity. We add artificial viscosity in order to preserve the monotony of the scheme, because in general this is not monotony. And the state of work of this project, actually, we have implemented everything. The 1D, the 2D, and the 3D model are perfectly working, but it is under testing because we just wanted to improve the model to be work in the parallel framework. And then we are finishing also to calibrate all the parameters of the models. But before going to the next example, I want to show you a result of this experiment, which is just a benchmark test, because this is the graphics. They are the graphic of the porosity of t equal to 0 seconds, and then after 2 days. As you can see, the border is shrinking, so everything works fine. This, I just want to remark you that this is a benchmark test because we use a value of Kw AKC very high, because the exchange rate in general is a very small constant. It's like, it's around 10 to the power of -3, so it is very slow. For this experiment, we use 100, which is very, very big. And that's why we can see this evolution in very short time. But in general, if we wanted to see a coherent example, we just put back our constant K to 10 to the power of -3 and just wait more time, because we needed to wait more for the penetration of the carbonic acid and the reaction to lose material. Okay. Then the last the last part of this presentation is going to be about the main project of my PhD thesis, which is a multigrid solver for 3D stone sulfatation model, which is the 3D stone sulfatation model is a model discovered by Driollet, Daniele, and Natalini. But what we want to do is to improve this model and have and use the multigrid approach with the level set and the ghost point strategy to solve the system, which is also here a reaction diffusion model depending on the marble and the sulfur dioxide and also the porosity. Here A is just the constant of the reaction of the chemical reaction. So just to give you a small insight about what is multigrid, if you don't know what it is an algorithm that solves also. It is an iterative method for linear systems that is based on two principles: the smoothing principle and the coarse grid principle. So actually, what we do is we just smooth the error. We solve the system using a smoother, and then we project the error on a coarser grid. This is because if we look at if you look at the error on a coarse grid, actually it is well approximated, and also we have less point to solve the system. We have less point that are used to solve the system, and that is just a scheme of the multigrid. So we start from the highest grid possible we want to use, then we smooth, we extract the residual, and we project it on a coarser grid. For example, we just double the space step, and as you can see in the picture here. And so we do again, we smooth sometimes, and we project, we smooth again, we project, until we reach some points, for example, where we have a system which is, for example, of the size 10 times 10, that which we can solve directly with very fast methods. And then we go back. We just correct every residual evaluated before. And then we have the final solution. But if it doesn't reach the convergence, we just repeat again everything. In the multigrid, there are two main or most used cycles. The first one is the V cycle, which is actually this picture, as you can see. So we start from the finest grid, we go down, and then we go up. With the second one, which is the W cycle, we go down, solve a system, we go up, we go down again, we solve the system, we go up, and we just do some up and down until convergence. The difference is, of course, the time, because the W cycle is more time consuming, because you have to perform many iterations for smoothing, and also you need to solve for linear systems. in this example, so you can have a different shape for the W. But the very advantage of the W cycle is because it has a faster convergence rate. And what we want to do in this project is to, well, firstly, we want to test everything in the context of the Poisson equation, and just to be sure that level set, ghost point, and multigrid are compatible each other, because in the multigrid approach, you need for each level to solve the ghost linear system every time, because each grids has actually they have at some points the same ghost points, but maybe there are some points which are ghost on the finest grid, but not on the coarsest. And then we want to apply this solver in the context of the 3D marble surfatation model and study a preconditioning, a good preconditioner of this in order to have a faster, in order to increase the speed of the solver, because it is very, very time consuming, a solver of this kind. So this is the last topic of this talk. This is a list of references used to write this presentation. And what I want to say to you is thanks for your attention.
Thank you, Samuele. So, question?
I have two questions.
Yes.
First of all, when the porosity is like increasing, basically the boundaries are moving, right?
Mm-hmm.
So does that mean for each time step you recalculate the field?
Actually, yes, but in an implementation way, you can avoid to calculate again everything, because on the outside point, on the external point, you don't need to evaluate again. So yes, you evaluate again all the level set, but not all points as the first, as the initial condition.
So basically, I use the file just to check which points getting updated as.
Yes, and also you can maybe predict the next, the value of the next point using an interpolation between between two timestamps.
Another question I have is about the ghost point itself. So I imagine if I have a specific order method, then if I interpolate it also in a specific or even higher order scheme, it would have the same order. But what about like stability? How would that get influenced?
Can you please repeat the question?
For example, if I have like a normal grid and I have like external and explicit method, I should have like a CFL condition. But if I apply then this level set method with even the moving stuff,
yes,
I would interpolate. But how would that influence maybe like stability or?
Actually, since they are virtual points, they should not interfere with the stability.
Okay.
So there is a question from. Oh, sorry.
You can also read the past was a question.
Past was a question.
Okay. So the approach is that you can actually have you can use actually it is an easier tool to solve the system. Actually, transforming coordinates, you need to have a matrix of the transformation. So for each point, you need to to multiply with that matrix. But maybe this can be harder with strange shapes. Maybe if your boundary has a cuspid point, this can be hard to perform, or maybe with some holes inside your domain. The level set ghost point can be very useful in this sense.
Don't worry.
So since the level set seems to rely on interpolation, questions. Yes. How do you address the potential impact of the Runge phenomenon on the dynamics? Actually, we didn't study it. At the moment, we just see that this method.
Samuele is replying to Mario Pezzella's question. Sorry.
No. Actually, we don't look at it. Actually, it is useful. We should study it, the Runge phenomenon. And actually, what I can do about the stencil is that you need to take some points in both directions, because For example, if you are in 2D and you use a stencil of 9 points on the same line, the matrix is going to be ill-conditioned, and so everything goes bad.
I guess. Oh, sorry.
Yeah, it's waiting.
I will just, I'm not a specialist from this field, but I would just point out a thing. So we are evaluating the boundary, which is when the porosity reaches 1, right?
Yes.
So that the material is completely dissolved. But which is two questions. The first one is how can you measure the advantage of using this point with respect to regular grid, for example? So if the discrepancy, how can you, if you have some plots or something like that to show us how much it is beneficial? And the second question is what happens if, for example, this boundary line, this boundary surface is very steep. For example, it cuts between 2 points of the grid or stuff like that, because it's quite challenging in that situation, because you have 2 points which are close and they are both considered as single points, but then you could have some gap between them.
Yes.
And then you can form, for example, cycles and cocycles of points inside your material. So which are these?
So about the first question, at the moment we want to study also that the situation, because it is not so easy to understand. About the geometry, actually it is more challenging during the implementation. There are, for example, if you have one ghost point and you have a boundary that goes in this situation and it should go in both directions, actually you will have a double, twice that point, 2 times that point, because you need one for the left side and one for the right side.
So you are classifying the same point as both the internal and the ghost point?
No. The external point is going to be only the ghost point. The internal...
Just to, because maybe... Suppose you have this grid, and then you have something like this.
No.
Okay.
To solve this kind of problem, you need...
You have these are both internal, all of them are internal, but then you have that they should have some gap.
No, in this case you need a better refined grid to catch that that cutting
so
inside.
So you are still getting that at some point you will have some jump, because, for example, I mean, with all purpose, if I understand it well, is that you want to avoid the cell jump, meaning that first you have a cell, then you don't have it anymore. But in this case, if, for example, I don't know, this happens, abruptly this point disappears from the space and you are not predicting it.
No.
Okay. Thanks.
Maybe, last question. So the only point, I think you have used the invertibility of H is when you define this U star.
Yes, this is the only point. And that's why you need that good stencil, because in the other case, H is going to be or a diagonal or at most, or in the worst case, singular. Because suppose you have literally a one-line stencil, so the interpolant polynomial is going to be of 1 dimension, not 2-dimensional. And so because of this, maybe the weight of the ghost point drops to 0, and this is what we want to avoid.
Thank you. So you received many thanks and congratulations. So thank you again. And see you next time.